For chapter 4, we're looking at trigonometry. So we're going to start off with the basics of the circle and the unit circle. Today we're just going to do a lot of terminology, so I'm not going to cover too much of it in detail on the video. You can look over the definitions easily in your book as well. We'll talk about it a little bit though. Okay. Triangles, ancient Greek, three angles, you don't care. The idea is it primarily was used for relationships between those triangles, but the angles are what we're going to focus on in this chapter. There will be some triangles, but it'll also be angles within a circle. Okay. Now, just so we have the terminology coherent between everything, we're going to look at any angles made out of two rays, the endpoint where they meet to that vertex. The idea is we're going to always set these up oftentimes on an XY axis. Because of this, we have what's set up as standard position. Your initial side is always on the x-axis, and then your positive angles are rotating counterclockwise, your negative angles are rotating clockwise around the circle. Okay. We will also be using both degrees and radians. We'll use radians most of the time though, because the nice thing about radians is it directly relates to how far you're going around the exterior of that circle based on what that central angle is. Okay, so one radius, you end up with all the same measures from the center out as you do on the angle. The central angle being from the center, the measure of the angle around it. Well, you will use these extensively in calc, so get them memorized. Radian measure in general, you can always find by taking the length, or the angle measure I should say, you can take the length of the arc, which is S, so the length of the arc here divided by what that radius is. That'll give you the angle. Honestly, most of the time we're going to be working with the primary ones on that unit circle, pi over 3, pi over 4, pi over 6, things, multiples of those. But you do always come up with the fact that all the way around a circle once is 2 pi. So however many rotations you have, it's 2 pi times the r. That's the overall distance around. Okay. And the 2 pi is 6.28, and all this definition stuff is in the book. And I already talked about a little bit, those common angles that we will use are those where you have pi over 6 or 30 degrees, pi over 4, 45, pi over 3, pi over 2, pi and 2 pi, and multiples thereof in each quadrant. So the nice thing is, we can actually find what are called coterminal angles. So if I have a positive angle that's 9 pi over 4, if I subtract 2 pi from it, it gives me a coterminal angle. Now, since it's over 4, when I do 2 pi, I'm actually going to be subtracting 8 pi over 4, which is just going to give me pi over 4. If I'm doing 5 pi over 6 as a positive, and I want a coterminal to that, I can actually add or subtract. But if I subtract 2 pi here, it's going to be 12 pi over 6. So when I subtract 5 pi over 6 minus 12 pi over 6, that's going to give you negative 7 pi over 6. And if I want the negative angle for this one, I'm going to take starting with the negative angle, if I want to get a positive angle, I'm going to add 2 pi. And since it's over 4, we're going to add 8 pi over 4, giving you a total of 5 pi over 4. Okay? Should be reviewed. Everybody should be fairly comfortable with this stuff. Now, radian measures, when you start dealing with them, you have two positive angles, alpha and beta, that are complementary to each other if they add up to pi over 2. Complementary add up to 90, complementary also add up to pi over 2. Supplementary is normally 180 degrees. Supplementary, if you're doing radians, is just pi. So, if I want to find the complement and the supplement of these two angles, well, pi over 6, the idea is since they have to add up to pi over 2, well, I'm just going to be thinking about the fact that pi over 6 is right here. Well, what's left here? Well, since they have to add up to pi over 2, I need to add pi over 3 here, or 2 pi over 6. So pi over 3 is the complement. 2 pi over 3, the problem with 2 pi over 3 is it's already more than 90 degrees. So it's here, so it has no complement, yep. So this one just has a supplement. So since this is 2 pi over 3, and I'm going to pause the video for a moment. And I'm back, but you gotta love when they start rehearsing for the marching band while I'm trying to record these lessons. Anyway, So, where was I? Supplementary angles. You do not have a complement in this case. You only have a supplement because it's greater than 90 degrees. So, the idea though, because all this has to add up to be 1 whole pi, this one has to be pi over 3. If I go back to this one, pi over 6, that makes it fairly easy going all the way around from here. The supplementary angle would be 5 pi over 6. Okay. Using degrees, the nice thing is if you want to convert, it'll always be this consistent. The way I always remember it, if I'm using degrees, if I have degrees and I want to get radians, that means I'm going to add pi to it, so I'm going to have to multiply by pi and divide by 180 to reduce the numbers. If I want to convert from radians to degrees, I want to get rid of the pi, so I want to divide by pi to cancel it off and multiply by the 180. Okay, so this gives all your nice conversions right on one page if you have that. So if I want to express each one of these as a radian measure, well, I'm just going to multiply by, because I want to be a radian, that means I want to add pi in. So pi is going to be on top when I multiply, and 180 is going to be on the bottom. So then I just end up with pi on top, 60 and 18, or 180 I should say, or 6 and 18, leaves you with 3. 320, I'm going to do the same thing, times pi over 180. I'm going to have pi on top. The zeros will go away. 32 over 18 will reduce down to 9 on the bottom and 16 on top, or 16 pi over 9. So it's not a normal unit circle one, but it is an exact value that you can find. Negative 30 degrees. For that one, if I again do pi over 180, or just realize I'm going down 30 degrees, well, that one's just going to be negative pi over 6. Okay. Now, if I want to go the other way, pi over 6. Express the following angles in degree measure. This one is just that common one. I would honestly expect you to know that pi over 6 is 30 degrees. 5 pi over 3 is a little bit harder to spot, so I'm going to multiply by 180 over pi. When I do that, the pi's cross off. 180 and 3 simplify out into 60 and 5. In other words, 5 times 60, 300 degrees. 3 radians is a little bit odd because it's not a nice clean number, but it still works the same way. They'll actually write radians on that a lot oftentimes when they don't show the pi, just so you realize what it is. But radians doesn't have a symbol. So if I take 3 radians, I'm going to again multiply by 180 over pi. Well, 3 times 18 is going to give you 540, or 54, 540, over pi. Punch this one into a calculator, you will get 171.89 degrees. Okay, now some of the applications of this. We will be using some word problems with this stuff and applying these to some situations with circles. One of the main ones you need to know is that your arc length S is equal to the radius times the angle that's traveling through, that central angle. Okay. Oftentimes if you're on the unit circle, it makes it very, very easy because it's just going to be the same. The radius is 1, that S is just going to be whatever theta is. And that's the nice thing about the unit circle. So, if I have a circle though that has a radius that's bigger than that, in other words, I have a circle with a radius of 27 inches, and I want the length of the arc intercepted by a central angle of 60 degrees. I'm going to use that S equals R theta, and I'm just going to mentally think of the fact I have a circle here, pretend it's a circle. Over here is your initial, your terminal is going to be 160, well that's going to be about here. So what they're asking is how long is this line when this is 27 inches long? You have 160 degrees and 27 inches. So you just multiply these values together. Now, the problem is, can I use the 160? It needs to be in radians for this to work. So I do need to convert this. So I'm going to take 160 times, because I want to get the pi in there, it's going to be pi over 180. 18 and 16 simplifies down to 8 and 9. So I have 8 pi over 9. So I'm going to take 8 pi over 9 is the angle, should have left myself some room, times 27. When I multiply these, 27 and 9 gives you 3 and 1. Multiply that through, you get 24 pi, which that would be your exact answer, and your units would be the same as the radius, so 24 pi inches. Or if you punch into a calculator, you're going to get 75.4 inches. Either way is fine if it doesn't specify. A couple other formulas that do come up, and you will use these, just not as much. It's mainly realizing how they work. Linear speed is the velocity around the outside. Since you're going around the outside, all that is your arc length around the outside of the wheel or circle or whatever you're talking about, divided by the time. Okay? Angular speed is just going to do the same thing, except for it's going to look at the angles that are being traveled through. And all this stuff needs to be in radians, otherwise these formulas don't work. So you're just going to take whatever that central angle is, theta, divided by time. So, if I have the second hand on a clock that is 8 centimeters long, I want to find the linear speed of the tip of the second hand as it passes along the clock face. So how fast is that tip going? Well, for this, that's linear velocity, so that's going to be the arc length times divided by time. Well, conveniently, or the time, I'm just going to use 60 whole seconds to make one whole revolution. So that means the S, I'm going to convert here and use that S equals R theta. I'm going to plug in 8 centimeters, and theta, since we're going all the way around the clock one time, is going to be 2 pi. So that gives me 16 pi for the actual arc length in this case. So that's 16 pi. And find the linear speed, well, in 1 minute, in other words, 60 seconds, I end up with 16 pi over 60. And this is the units on these as well. This is centimeters for arc length per second. 16 and 60 simplifies down to 4/15 and pi attached. And if you approximate the decimal to that, that's 0.838 centimeters per second. Another example of this kind of problem that shows up often: circular blade on a saw rotates at 2,400 revolutions per minute. Find the angular speed in radians per second, and then the blade being having a radius of 4 inches. Find the linear speed of the blade tip. Okay, so first off, I'm going to use, and I didn't mention this earlier, the symbol they're using here is the Greek letter omega. It's the lowercase version. You might be familiar with the uppercase version of omega. This is the lowercase version. Okay, that's kind of what it looks like. I can't draw it perfectly, but anyway, for that, that's going to equal your angle in radians divided by your time. So now this one's a little bit strange because of the way it's written, but it's not too bad. Because if I take 2,400 revolutions, I need to figure out the angle that travels through. One revolution is 2 pi. So 2,400 revolutions times 2 pi gives you the number of angles it's traveling through in 1 minute. So that's what I'm going to set up. 2,400 times 2 pi is going to be 4,800 pi divided by 1 minute, but I want radians per second, so I'm going to put that over 60 seconds. Okay, so clean that up a little bit, take away one of the zeros. 48 divided by 6 is going to give you 80. 480 divided by 6. So I have 80 pi, and that's going to be radians per second. So from there, that's your angular speed. For the actual linear, I need to figure out how far it actually travels along that outside. So I'm going to take that 80 pi radians times, and I'm going to generate the arc length for this, the radius, so 4. Multiply those out, you end up with approximately 1005.31 inches per second. One other common formula comes up that you will want to know as far as being able to figure out the angle. I usually modify this a little bit because you don't need it exactly the way it is. But the area is going to be equal to area of a circle, so it's kind of like a pizza slice, is 1/2 r squared theta. Okay? Well, you can cheat this one a little bit. I modify it a little bit. Area of a whole circle is pi r squared. Okay? So what you can do for this is actually do the same thing, pi r squared for the whole circle, and then do whatever fraction you're talking about. So you're going to take theta over, so this is the area of a circle, this is the area of a sector, is theta over 2 pi, so that fraction of a circle, times pi r squared. Some people like doing it that way. You can actually see really quickly, the pi just cancels off. You still have your theta up here, and you have 1/2. It's the same formula, but I usually don't bother memorizing this because this one works and does the exact same thing. It's a lot more intuitive. So if I do that one for this problem, sprinkler on a golf course is set to spray water over a distance of 75 feet and rotates on an angle of 135. So just a rough sketch of this real quick. 135 degrees is a little bit past 90. This isn't to scale, that's fine. It shoots at 75 feet, so that's your radius. I want to figure out the angle covered by this sector. Well, it's a fraction of a circle. I don't even need radians for this. This is the really great thing, because I can set this up as your area is equal to that fraction of a circle. 135 over 360. Because that fraction of a circle, I can actually just then take times pi times the radius, which was 75, squared. Now when I do that, I can type that all into the circle as one thing. So 135 divided by 360 times pi times 75 squared. You end up with, it doesn't specify the area, so let's do 6,626.8, and the units, because we're talking area, are going to be square feet. Okay. Now, the half sheets everybody should have. I'll leave a few copies with the sub if anybody needs them. They will also be posted on the back and the front wall. So, you have the time, make use of it. Get to work.